Hello and welcome to the session on GaN characterization and modeling using ASM-HEMT. My name is Ahtusham Pampuri and I'm from Nanolab, IIT Kanpur. We'll start with the contents. So I'll introduce my lab and then we can talk about the model and how we can use this model for different types of devices like power devices or RF devices. And then we'll also talk about how self-heating is characterized and modeled using ASM-HEMT and also about trapping models in ASM-HEMT. I'll start with a brief introduction about Nanolab and all the characterization and modeling capabilities we have. So these are some stats about our lab. So we have been publishing a lot of books, journals, conference papers, and at present we have around 5 postdocs, around 27 PhD students, and 10 PhDs have already graduated. And our source of funding usually it comes through government agencies, industry partners, and the Compact Model Coalition. This is a brief list of all our industry collaborations. We work with universities, with public sector entities, with private sector entities, both in hardware and software. At Nanolab, we work all the way from the atomistic level to the circuit level. So we cover materials, we cover devices, we cover modeling, characterization, and eventually circuit design. For characterizing devices, we use a wide variety of equipments, mostly from Keysight. So these are some of the equipments we have in our lab. So we have a Keysight B1500A, which is a semiconductor device analyzer. It measures the IV, CV, and even does pulsed measurements. And this here is a Mori Microwaves AM3221. This is a pulsed measurement system which can go up to 25 volts and 1 ampere currents at gate, and you can go as high as 250 volts and 30 amps at the drain. For RF measurements, we have a Keysight ENA, which goes all the way from 100 kilohertz to 8.5 gigahertz. And for high frequencies, we also have a Keysight PNA-X in 5244A, which goes all the way from 10 megahertz to 43.5 gigahertz. For measuring devices which work on high currents or under high voltages, we have a Keysight Power Device Characterization System, B1505. Then we also have a noise figure analyzer from Keysight, the N8975B, which goes up to 26.5 gigahertz. And we have a state-of-the-art passive load pull system from Mori, which we plan to expand in the near future to a complete 3-harmonic hybrid load pull system. These are some of the unique capabilities we have. We have SPICE simulators from all the major EDA vendors, some RF circuit simulators, TCAD simulators, and also atomistic simulators. That was all about Nanolab. So the next thing I'll do is I'll introduce the ASM-HEMT model. We'll talk about the core of the model, its extraction flow. We'll talk about the add-ons we have incorporated into the core. We'll talk about how the model is able to capture geometric scaling. So this is a brief history of all the HEMT models, and among these models, Angelo has been quite famous, at least when it comes to GaN HEMTs. Now these are the various classes of compact models. Compact models can be table-based, they can be empirical, or they can be physics-based. Now table-based models are simply measurements, a lot of measurements which are taken from a device and then they're used as a model directly. And empirical models, they're basically models which try to emulate a device using simple equations, simple mathematical equations. They're not derived from physics, and as such, you can't expect them to be scalable or to give you any insight about the device. Then come physics-based models, and they are also divided into 3 categories. Some can be threshold voltage based, some can be surface potential based like ASM-HEMT, and some can be charge-based, like the MVSG model from MIT. So now ASM is basically Advanced Spice Model for GaN-HEMTs, and if you want the code or the documentation, you can visit the following link. Let me introduce the team. So we have Professor Chauhan and Professor Khandelwala as the directors, and we have almost 5 developers, out of which me and Raghavendra are currently working on the project. This is a brief summary of how ASM-HEMT works. So this gives a proper overview of the model. We start with the electrostatics, where we solve the Schrödinger and Poisson's equation, which gives us the two-deck charge, the Fermi level, the surface potential. Then these quantities are then used to derive the transport of the device, which is a Griff diffusion-based model. We get the IV, CV, and all the second-order effects. Then we have some higher-order effects like noise and crapping and self-heating and field plates for power devices, which are then incorporated, and they help us emulate a real live device. Okay, so this is the current expression which we use, and this basically is dependent on the source side and drain side surface potentials, which come from, again, as I said, from the solution of Schrödinger and Poisson's equation. And then we incorporate effects like mobility degradation and velocity saturation. This is the final drain current expression we get. Then to this drain current model, we then incorporate other effects like I said, mobility degradation, temperature dependence, field plate capacitance, scrapping effects, subthreshold slope, the flicker and thermal noise models, velocity saturation, Dibble, self-heating, and this is something which is quite common in HEMTs, in GaN HEMTs, is the access region resistance, because unlike MOSFETs, the entire space between the source and drain is not the actual device. There are some regions which are not under the gate, and they offer nonlinear resistance which has to be modeled accurately. Then we also have a gate current model incorporated into the core, and these are some of the parameters which are used to define the core model. Now this is an overview of the extraction flow of the ASM-HEMT model. We start with the device dimensions, and we set the length, the width, the number of fingers, the thickness of the AlGaN layer. Then the first thing we extract is the subthreshold characteristics. So we extract the threshold voltage, the N factor of the device, the drain dependence of the N factor, the eta, which is the Dibble factor. We extract all of this from the subthreshold region. Then we move on to the linear region. Then in the linear region, we extract the mobility and its dependence on gate voltage through degradation parameters like UA and UB. We also extract or start to extract the drain side access region resistance. Also in the linear IDVG, we try to improve the eta we had extracted in the previous step. And once that's done, then we move on to the output characteristics, which is the IDVD. Then in the output characteristics, we extract the CLM, which is lambda, and we extract the saturation velocity. We again tune the eta, which is the Dibble factor from the IDVD. And it is in IDVD we properly extract all the access region parameters, and then we also extract the self-heating model, which we'll talk about later. After we have done the extractions at the nominal temperature at which the measurements have taken place, then we go for the temperature parameters, and then eventually the final step is modeling the capacitances. Now this slide offers a visual representation of the extraction process. the process which described in the last slide was a summary of all these steps. So the first step we discussed was the subthreshold characteristics, and in the subthreshold characteristics we extract a few parameters like V off, which is the off voltage or the threshold voltage, and then the N factor, which is the subthreshold slope, and CDS/CD is the drain bias dependence of the subthreshold slope. As you can see, the subthreshold slope changes with different drain bias conditions. So these are the few parameters you extract, and there's another parameter called eta naught, which is the Dibble parameter, and this basically gives you the spread in drain current with respect to drain voltage at a given VG. So once we have extracted the eta naught, we can refine it in the subsequent stages, and by subsequent stages I mean the linear transfer characteristics and the output characteristics. So the next step is then the linear transfer characteristics. In the linear transfer characteristics, just after threshold, we extract the parameter U naught, which is the mobility parameter, the low field mobility. And in high gate voltage regions, we extract the mobility degradation parameters, which is UA and UB. So these two parameters are extracted in this region, and these two parameters basically give this tapering you see in the drain currents. And this tapering is also caused by the drain side axis region resistance. So basically at this point in this region, in the high gate voltage region, you sort of you try to extract three parameters. One is UA, UB, and then the drain side axis region resistance. And then all of these can be fine-tuned in the subsequent steps. Okay, moving on to the next step, which is the output characteristics. So in this region, as you can see, we again fine-tune the drain side axis region resistance, which gives you the resistance of the IDVD curves, and also the saturation velocity and other parameters, like again you can fine-tune UA or UB in this graph as well. And once that's done, once this is for saturation velocity, once that's done, it's almost in the low drain voltage region, there's almost a good fit. And then what's remaining is the high drain voltage region. So for the high drain voltage region and high currents, that's the region where a lot of power is generated, and because of that power you have a lot of heat generated, which activates the self-heating system, which we are going to discuss later. Then at this point you extract the thermal resistance of the device, and that gives you a final fit. So to summarize all the points I already made, and now these are the parameters we mainly work with in these regions of the characteristics, of the IV characteristics. So eta naught, N factor, CDS/CD, V off in the subthreshold region, U naught, UA, UB in the linear region. And for the output characteristics, there are a number of parameters. VSAT, UA, UB are fine-tuned. Then NS naught ACCS basically is the 2-day concentration in the axis region on the drain side. So changing this basically changes your drain side axis region resistance. And VSAT ACCS is the saturation velocity of the axis regions, which again, as you might know from the physics, the axis regions also have a 2-day in them, so they have a certain saturation velocity. And then the axis region resistance mobility at the drain side and at the source side as well. All right, okay, so the next, now that was the core model we discussed about. The next part is the add-ons. We talked about add-ons. So the first add-on we're going to discuss is the bias dependent axis region resistance. So this is how it's modeled. We have an intrinsic transistor, and then at both the source and the drain end, we have two nonlinear resistances, added in series. So this is basically a simple SPICE circuit which is there in the Verilogix code. Two nonlinear resistances added in series to an intrinsic model. And how this has been modeled is you simply take the current as charge into velocity, and then the velocity is saturation velocity into a certain quantity which denotes the saturation in that region. And if you rearrange this, and if you define the resistance as the drop across the resistive part and the current flowing through it. Now note that this current should be the same as the current flowing through the intrinsic device. So once you define the access region resistance by this number, RD or S, depending on whether it's the drain side or the source side, you have an equation which looks like this, which depends on the drain current and the saturated drain current. Now the saturated drain current is a fixed number because the saturation velocity determines it, and the drain current is the same as we discussed in the previous slides, the drain current from the core model. Once you put all those numbers in, then SPICE automatically solves this circuit and you get something like this. So this is the output. With increasing drain currents, as you would expect, the resistance increases. What that means is, as you increase the drain current, since the now this region is velocity saturated, so it is limited by its velocity saturation. So as you go on increasing the drain current, you see higher and higher resistance because there's a limit to which it can conduct, right? So, okay. Okay, so now this slide talks about the effects of the bias-dependent access region resistance. And mainly there are two effects. The first effect is in the transconductance of the device, and the second effect is in the output characteristics of the device. Now, in the transconductance, you'll notice that there are two slopes in this transconductance, which is a very, a signature of GaN-HEMTs. Since they go to very high currents, you clearly see those you clearly see these two different slopes. And the first slope is because of velocity saturation. So in the transconductance, the first slope you see is due to velocity saturation, and the second slope, which is normally at very high gate voltages and at very high drain voltages as well. This is because of self-heating, and as we know, self-heating manifests itself in high gate and drain voltages, which basically corresponds to higher currents and higher power and more heat dissipation. And the second effect of this access region resistance is what is called quasi-saturation. So the quasi-saturation model, it's not a model, but the quasi-saturation effect basically manifests again itself in a region where the currents are very high and the gate voltage is very high. So you see this bunching of different gate voltage curves together. This is what's called a quasi-saturation effect. So basically, in this region, the device is limited by the device current is limited by the access region resistance. Now the next thing we're going to talk about is the temperature scaling of the access region resistance model. As we mentioned before, the access regions basically are regions with a two-deck concentration. You can think of them like transistors without gates, but they still have a two-deck which allows the electrons to flow. And because of this two-deck, they have a certain temperature dependence. And the ASM model, it captures that temperature dependence through these three equations. So the first equation governs the temperature dependence of the access region two-deck concentration. So this defines the temperature dependence of the access region 2-deck concentration. The other effect is the temperature dependence of the saturation velocity in the access region. And the third effect is the temperature dependence of the mobility in the access region. So these three effects combined provide a very robust temperature dependence model, as you can see. So these are the measurements at different temperatures of the on resistance, and this is the model. So it really very accurately captures the behavior. Now we talked about the temperature dependence of the access region. There's also a temperature dependence of the core model itself, since the core model also has a 2-deck layer, and that 2-deck layer basically the 2-deck has a certain temperature dependence which needs to be captured. So this is the temperature scaling, the model and the results of the ASM-HEMT. In the model, the temperature scaling is defined by three main parameters or three main equations. The first one governs the off voltage of the transistor, and the second one is the temperature dependence of the mobility, and the third one is the temperature dependence of the saturation velocity. And using these three equations, what we get is a very accurate model for the temperature scaling of the main transistor. And as you can see, these are the temperature results for basically two different temperatures. So this is at 100 degrees and this is at minus 20 degrees. And this is the transfer characteristics at 100 degrees and at 20 degrees. You can see the model perfectly scales from sub-zero temperatures to almost 100 degrees, which is pretty much the normal temperature for power devices. We talked about scaling in the ASM-HEMT model, which is really a key feature of all physics-based models, and that is the ability to scale. So in ASM-HEMT, there is scaling incorporated in different aspects. There is scaling incorporated in charge. So the gate charge and the drain charge is scaled according to the width of the device. And the source charge is basically just is calculated using charge conservation. So QS is basically just minus QG minus QD. Scaling is also incorporated in the current equations. So all the currents are scaled, and the access region resistance is also scaled. So you can see the source resistance and the drain resistance have a proper scaling factor incorporated. The noise models in ASM-HEMT are also scaled with width as well as length, which is also the case for all the previous models we talked about. And there's also scaling of length and width in the gate current. So all of these different models, these scaling parameters in these models allow ASM-HEMT to be a properly scalable model. So that was all about the ASM-HEMT model and all the add-ons we have in ASM-HEMT. The next section we'll talk about the different applications in which ASM-HEMT can be used, and the first among them is power devices. We'll see how ASM-HEMT is used to extract parameters for power GaN HEMTs. It starts with modeling the DC of the device. Then power devices normally have field plates, so we'll see how those are modeled in ASM-HEMT. And then we'll see how the model performs, or what the results are when we compare it to a mixed mode simulation, which is basically a TCAD simulation. Now, just like we we talked about in the previous section. So we start with the DC extraction, and we already went through all the steps of DC extraction. So these are just some of the results of the extraction we did for this device, which was a power device, power GaN device. And you can see that it really overlaps with the measurements. The model really overlaps with the measurements. Even in the derivatives and the second derivatives are very closely matched. So this is the output characteristic. This is the derivative of the output characteristic, which is GDS. And this is the second derivative, which is GDS prime. Now these are the reverse output characteristics at 25 degrees Celsius. And this is again the derivative of the reverse output characteristic and the second derivative of the reverse output characteristics. Again, as you can see, it very very accurately follows the measured data. And so the next slide is going to be about the input or the transfer characteristics of the device. So as we can see at 25 degrees, again overlapping with the measured results. The first derivative, which is the transconductance, and this is GM prime, which is the first derivative of transconductance, or the second derivative of the drain voltage with respect to VG. And these are some of the log scale results. Now this is the log scale result for the output characteristics. This is the log scale result, or what we call the subthreshold characteristics of the device. Again, a very perfect match. And these again are the reverse output characteristics in log scale. Now what we saw till now was the extraction of this power device at room temperature. Now in order to move forward, we need to extract the parameters for different temperatures, and for this we use the parameters we talked about earlier when we discussed temperature scaling of the core model. So basically 3 different parameters. One is the parameter for V off, the other one for mobility, and the third one is for saturation velocity. So using those 3 parameters, those 3 temperature dependence parameters, we can then extract the model for different temperatures. Now this result is for -20 degrees Celsius, and you can also, in this you can see it's again very accurately matched to the measured data. Again, the same graphs, the derivative and the second derivative of the drain current. And this one is the log of the output characteristics. These are the reverse characteristics, and again the log, the derivatives, and we can see that even at -20 degrees, the model is able to accurately capture the characteristics of the device. Now this is the transfer characteristics of the device at -20 degrees. Remember that this is again the same model card. You have not changed anything except the 3 temperature dependent parameters, and you get a very good fit up to the second derivative of the transfer characteristics. And this is the subthreshold characteristics, again a very good fit. Now this is at a very high temperature. As you can see, the model is very accurately able to capture the characteristics at even 100 degrees Celsius. And again, the transfer characteristics, the output characteristics, they just match perfectly with the measured results. The next slide is about even higher. We go up to 150 degrees, and you can see the device, the model is able to capture the device characteristics very clearly. So you can see the dynamic range in terms of temperature scaling of the ASM-HEMT model. We can go we have validated from -20 to 150 degrees Celsius, and we're sure the model will be able to go beyond that. It's just that we have not validated for data beyond this temperature. Now this next section is a key differentiator of power electronic devices. These structures are called field plates, and the reason they are used is because these devices, they operate at very high voltages. If we go by state of the art, I mean, they can even go up to 600 or maybe even 1200 volts. And given these high voltages, the drops in the device, especially at the region where the gate interacts with the drain voltage, which is the region just below the gate edge, is very high. So the drop in this region is very high, as you can expect. So there is an entire layer of 2DEG in the entire axis region. Then you apply a drain voltage, and this 2DEG layer, it behaves sort of like an equipotential surface, like a metallic surface. So there's essentially very minimal drop in this 2DEG layer. So that voltage, say for example 600 volts, is almost entirely carried up to this gate edge. And then if the gate is, say, at a voltage of -3 or -2 volts, then the entire 600 in -2 in the negative, which means basically 602 volts, the entire 602 volts drop is felt across this junction. Given there is no 2DEG concentration, that is if the device is off, then the entire drop happens across this junction. And there's a huge field in this region which can lead to breakdown, which can lead to a localized breakdown in the device. And to prevent this, now this is a heuristic which people have, which researchers have found out, is that they use what we call field plates. So basically you have these extra gate-like structures which you use, and it helps you to sort of disperse the electric field such that the device is still able to handle that voltage, but the electric field peaks are not that strong. Like we can see in this EV graph, in the EX graph. So this is position towards the drain, and this is the electric field. And this is the red one is the gate, is the foot of the gate. We're talking about, say, a T gate. And this blue one is the T part of a T gate, which also behaves like a field plate, like a gate field plate. And then we have another field plate which we have on top of this. So let's see what happens in this. If we just have this, if we have a non-T gate and we have a simple gate structure there, then all of the electric field drops across the edge of the field, the edge of the gate, and there's a huge spike in the electric field, and this spike can cause a breakdown in the device. Now we know from the electrostatics that if we integrate this field across the entire region, we get the voltage drop across this whole region. So the goal here is to minimize this peak, but to keep the area under this curve constant. That's exactly what's achieved using field plates. So for example, you have this T-shaped gate which behaves like a gate field plate. Then you have two peaks, the first peak at the foot and the second peak at the head, which happens because of a voltage drop across this region. Now as you can see, the peak electric field is dropped, but then your entire graph has now shifted in the direction of the drain, such that you still have a good amount of area under the curve. So your device can still handle that voltage, but now it is not, it's not reaching that critical electric field where it can break down. You can even get a better performance by using another field plate, so it distributes it even further, and you get even better performance. But there's a trade-off, and that trade-off is in terms of the capacitance. So you have to see what that capacitance does to your performance. And not only do you have to see, you also have to model that capacitance which is generated because of these field plates, and not just how the field plates affect the 2-deck, but also how they interact with each other, which is something which we call cross-coupling capacitance, which is also modeled in ASM-HEMT. Now, this structure here is a TCAD simulation, which basically shows the two regions where the electric field shows a peak. And in ASM-HEMT, the way we model this is by treating these regions as different transistors. So if you look at this region, it's just a gate stack with a different set of dielectrics. And if you see this region, again, it's a gate stack with a different set of dielectrics. And this region also is a different gate stack with a different set of dielectrics. So basically, if we talk about these field plates, we can have a normal transistor, then a region with a gate field plate, which can be modeled as another transistor in series, and then another field plate, the source field plate, as another transistor in series. And these three transistors then, in series, they behave like this complete device. So this is exactly how we model this in ASM-HEMT. So you have an intrinsic transistor, and you have another so the number of these transistors is user defined. You can define how many field plates you want. The current beta is it allows up to 4 field plates on the drain end as well as the source end. So you can have 4 field plates on each end. So this field plate now is a gate field plate. Since this is connected to the gate, again, this is user defined. You can connect it to either the gate or the source. It's your choice. But in this example, we're connecting it to the gate. Then there's another field plate, which is a source field plate, which is connected to the source. Then you have these access region resistances, which we defined earlier in the ASM-HEMT model. But now instead of connecting to the intrinsic transistor, they now connect to the last stage field plate transistor, basically. Now, as I mentioned earlier, field plates tend to offer capacitances which can then change device behavior. And these capacitances are very important modeled because eventually these power devices will be used in switching circuits, and switching circuits they react strongly to capacitive and inductive elements. So it's very important to model these capacitances accurately and to get their correct bias dependence. So the first thing we'd like to see is this graph, which talks about the 3 transistors we talked about. So T1 is the intrinsic transistor, T2 is the second transistor, and the T3 is the third transistor. These T2 and T3 are basically the transistors which are modeled due to the field plates. These are basically field plates modeled as transistors. Now, what we see is as drain voltage increases, and the device VGS is -15, so the device is switched off. So T1 is already off, as we can see. So T1 is already off and T2 and T3 are on. Then as you increase the drain voltage, the voltage at the drain of T1 starts increasing, which means the voltage at the source of T2 also starts increasing. And as the voltage at the source of T2 starts increasing, the VGS for T2 starts going down. And as VGS starts dropping, then T2 goes from on to off, as you can clearly see in this region. Then T2 stays off, and that voltage is defined as the cutoff or the threshold voltage of the transistor T2, which is again defined by the thickness of the dielectric under the second field plate. And similarly for T3, since the thickness of the dielectric is more, then you see an even negative voltage at which the device turns off. So eventually, at very high drain voltages, all three devices or all three gate stacks are turned off, of which T1 is the actual device and T2 and T3 are the field plated regions, which are modeled as transistors. Now let's see the effect of this behavior in the capacitance plots. Now this is the input side capacitance, which is nothing but CGS plus CGD. This is the input side capacitance. And as we can see, as T2 turns off, this goes down to zero, to a certain, no, not zero, but to a certain parasitic level. So this drop this happens exactly at a point where T2 turns off, which is somewhere between 25 and 50 volts of drain voltage, as we can clearly see here. So this is somewhere between 25 and 50 volts. And this is the input side capacitance. Now for the output side capacitance, for the reverse capacitance, which is CRSS, which is nothing but CGD, you can again see a very interesting trend. Now, if you just consider the T2, which is the gate field plate, as we discussed in the previous slides, you'll see that the CGD for that device goes down to zero or a certain fixed number at the voltage where T2 turns off. And for T3, which is the source field plated device, or the transistor which we converted from a source field plate, that switches off and the capacitance goes back to a fixed value at the voltage where the third transistor switches off, which is somewhere between 50 and 100. From this graph we can see it's almost 75, so it almost goes down to zero at 75 volts. And the CRSS is then, if we consider both these transistors, and then the combined effect looks something like this, which very cleanly overlaps with the measured data. So the red dots are the measured data, and it very cleanly overlaps with that. And this is the output side capacitance, which is nothing but CDS and CGD. Again, in this we see that the hump, which is formed by GFP, it terminates at the voltage where T2 switches off, and the hump, which is caused by the source field plate, it terminates at a voltage where the T3 turns off. Now this next slide talks about the trends with respect to temperature, and as we can clearly see, with increasing temperature, the threshold voltage of these devices changes. And by these devices I mean the three different transistors which we modeled from the field plates. We can see that due to temperature, the threshold voltage changes, then the characteristics shift in one direction. So as we remembered in the previous slide, we mentioned that these plateaus or these humps, they appear at voltages where the devices turn off. So if the voltages at which the devices turn off are governed by the threshold voltage, which they do, and the threshold voltage is a function of temperature, then these humps, they become a function of temperature. And as we go on increasing the temperature, these humps go on going in the negative direction. That is, the threshold voltage, it starts becoming more negative, and these humps start appearing at more negative gate voltages. Remember, this is gate voltage. The previous graphs we saw were of the drain voltages. Now these all three other graphs, these are for drain voltages, and as we can see, again, with increasing temperatures, these humps, they start appearing early, which means at lower drain voltages, which again, if we remember the structure of those transistors, this maps to a lower, to a more negative gate voltage. So these are the results for the field plate capacitances for different temperatures. Again, we see it very clearly follows the trends of measured data. Now, what we did here was we took the model which we extracted for the device, for that power device, and then we also recreated the power device using Silvaco Atlas, and we used that TCAD as part of a mixed mode simulation to simulate a power transistor in a circuit which basically is a switching circuit. So we created this switching circuit in mixed mode, and then we used that TCAD device to get the measured or to get the TCAD data for this simulation. And we had a supply voltage of 50 volts, and we had a fairly short pulse of 480 nanoseconds with 20 nanoseconds rise and 20 nanoseconds fall. And what we observed was that with the field plates, the ringing which we got was very accurate, and it almost overlapped with the mixed mode results we got. As you can see, if you look at this, then these are the turn-on transients, and these are the turn-off transients for the device. Now, the dotted ones are the results with the field plate model switched on, and the solid lines denote the results with the field plate models switched off. As you can see, with the field plate models switched on, the capacitances interact with the system such that there's a delayed ringing, and even the amplitude of the ringing is different, which is very important when it comes to switching circuits. And then we compared this result with the TCAD result we got from our device, and as you can see, it almost overlaps with the results, which is a very good fit when compared to the mixed mode TCAD output. Again, this is the turn-off transient, and these are the results with and without the field plate models. And as you can see, it really overlaps with the ringing. Even the ringing overlaps perfectly with the TCAD results. Now, as I mentioned earlier, the ASM-HEMT model also includes the cross-coupling and the substrate models for capacitance, and this really shows up in the current waveforms. If you look at these current waveforms for the drain current and the gate current, you'll see a very significant change, at least in the phase as well as the frequency of the ringing in these current waveforms. So the solid lines, these denote the results with the cross coupling and substrate capacitance included, and the dotted lines, they denote the results without the cross coupling and the substrate model. And the effects of that are again very clearly seen in the drain current and the gate current outputs from the mixed mode simulations. As we can clearly see, it very cleanly overlaps with the results from the TCAD. Now, the next section which we're going to discuss is the RF devices and how to extract a model card for RF devices using ASM-HEMT. Again, in this case, we'll start with DC parameters. Then we talk about the specifics of RF model extraction. Then we'll show some results for large signal and load pull simulations. Now again, we follow the same steps as we did earlier in order to extract DC fit for the device we have. In fact, the results I showed you for the core model were actually for an RF device. So I'm re-showing those results. So these, again, the same steps which we followed in the core extraction. and then you get a DC model card for your RF device. And then the next step is to do the extrinsics, and in the extrinsics we have three main components. The first one is to de-embed the manifolds of the device. So in any fabricated device, you'll have certain manifolds which help you connect to the drain and the gate of the device. And these are simply some metallic pads which connect the different, for a multi-finger device, these connect the different gates and the different drains together, and even the different sources together using air bridges or something. So the first thing you need to do is to de-embed those structures, because they add a certain parasitic element to the device, which will show up in S parameters, and you don't want to have that. The next part you want to do is to extract the intrinsic core model, which is the model without these manifolds. And we will do that using low frequency Y parameters, where we'll extract all the parasitic elements of the gate side or drain side, or the gate to drain capacitance. The third part we want to extract are the inductances in these paths, and we'll do that using high frequency Y parameters. This is a very short schematic of what we're going to do. As you can see, these are the gate manifolds and the drain manifolds, which basically help you connect to the actual device. And then these are the source manifolds, again metallic sheets or metallic pads which add a certain capacitance and a certain inductance to the overall device. And then after these manifolds, there are certain inductive components because of these lengths, and inductance mainly comes from a certain length of a metallic conductor. And these small inductances, we need to take them out before we go to the actual device, which is the intrinsic device under the gate and between the source and drain and under the gate. So in that device we have these specific parasitic capacitances which we're going to extract. The other intrinsic capacitances are going to be derived automatically once we have the DC fit. So once you do a DC fitting, we already get the charges right, and when you get the charges right, you get the behavior of those charges right, and the behavior of those charges basically determines these capacitances, which are the intrinsic bias dependent capacitances CGS, CGD, and CDS. So the bias dependent part is already covered when you extract the DC. The bias independent part of the intrinsic device is going to be extracted, as I said, using low frequency Y parameters. And we'll start with the extraction of the manifolds. So these manifolds, they're basically they're modeled as simple LC circuits. So in our case, we used two pi circuits for the gate side and the drain side, and a simple RL circuit for the source manifold. Then once you use these circuits, then you try to extract these numbers, the inductive, the capacitive, and the resistive components. You try to extract these numbers from the measurements using de-embedding techniques. There are many de-embedding techniques which can be used. The one we've used is TRL. We can also do an SOLT calibration, and that takes out all the parasitics due to these manifolds and pads. Now the next step we want to do is to extract the inductances from this device, and to do that once we have the device de-embedded, so we are at a plane which is after the manifolds, then we extract or we measure all the Y parameters of the device. So we have Y11, Y12, Y21, Y22, and once you have these, then you compare the model with these measured Y parameters at a very high frequency. And it is at a high frequency that you try to fit the inductive components, which are basically just inductances. You just have to fit them. You just have to tune the values of those inductances till you have a good fit at high frequencies. And then at low frequencies, we try to measure or we try to extract the overlap capacitances of the core model. So this is a low frequency log scale. The x dimension is frequency, and it's in a log scale. And then in Y, we're looking at CGS, we're looking at CGD, and then GDS and GM. So what we do is basically take this low frequency region and then try to tune parameters like CGDO, CGSO in this case. CGSO is the overlap capacitance parameter for gate source. CGDO is the overlap parameter for gate drain, and you simply try to tune these parameters so you have a good fit in this region. And this bias dependence, which is the trend you see with different biases, is actually captured automatically once you have a good DC fit. So this really makes ASM a turnkey solution, so that you just have to get a good DC fit, and these bias dependent parts, they're automatically taken care of. Then all you have to do is simply tune the overlap capacitances so you get these levels right. And it's really a very simple step to extract these overlap capacitances. And again, this for GM and GDS, it's just validation. Since there's not much you can do here, it should automatically fit into place as long as you have extracted the DC properly. So this should automatically fit, it should overlap with the measured results if you have a good DC fit. And the dispersion in the trap, the important part here is the dispersion we see here and the dispersion we see here. These are modeled by the trap model, which we're going to discuss in a few sections from now. Now this is the inductance fitting I was talking about. So these the inductance values, we tune them at a very high frequency, like for example in this case it's almost around 40 to 50 gigahertz. So once you have your core model, you have de-embedded your manifolds. Now all that's left to do is simply tune those inductance numbers so that you get these peaks right. And as you can see, again, it's a very good overlap with measured data. And just after doing this, if you simply compare your S parameters to your measured data, you'll see an almost perfect fit, as we see here for different voltages. So this one is for 5 volts, this one is for 20 volts. That was all for the RF extraction part. So what follows is the validation part. And as you can see, this is the validation for the harmonic balance simulations, and the model does a really good job at following and emulating devices in terms of their large signal performance. You can see it follows the measured data very cleanly, both the Pout, PAE, and gain. Small signal and the compression is accurately captured by the ASM-HEMT model. Even the time domain dynamic load lines, you can clearly see the dynamic load lines using ASM-HEMT if you want to. Now here again we have the validation of the model. Once you've extracted the DC and RF part, then this validation is for different load resistances and different load reactances. So basically the real parts and imaginary parts of the loads are both accurately captured by ASM-HEMT, and that too for different bias conditions. So this one bias condition is 20 volts in 10 milliamps per millimeter. These two are 20 volts and 100 milliamps per millimeter, and these are for the real parts. These are for the imaginary parts of the loads. So you can see a very accurate load representation and really overlaps with the measured results here. Now this slide presents the validation for load pull simulations. Now we used ADS for the extracted model, and we used the extracted model to perform a load pull simulation and then compared the results with the measured data. And as you can see, it almost overlaps with the measurements for different bias conditions. This one's again 20 volts, 10 milliamps per millimeter, 20 volts, 100 milliamps per millimeter, and you get very clean results. And this is very important for RF circuit design, because once you get these contours right, you get the impedances right, and once you get the impedances right, you have perfect matching circuits, which basically determine your RF performance. Now in this next section, we're going to discuss how to characterize self-heating and how ASM-HEMT captures the self-heating model. Now we'll talk about the model first, and then we'll talk about how it's characterized. The self-heating model in ASM-HEMT is defined what's called a thermal discipline in Verilog A. Now, in Verilog A, you can define things to be following the electrical discipline, or there's a different discipline like this thermal discipline where the flow of something is defined as power, and which would be the equivalent of current for an electrical circuit. Just like current flows in an equivalent circuit, in an electrical circuit, in a thermal circuit, the thing that flows is power. And like in an electrical circuit, you have voltage, which determines the potential between two nodes. In a thermal circuit, in a thermal discipline, that potential that voltage is actually the temperature. So if you look at this circuit, this looks like an electrical circuit, but it's not. So the current flowing through the circuit is basically the power dissipated in our device, and that power dissipated is then moved through two components. Basically, this is an RC circuit. So the resistive part and a capacitive part. This capacitive part gives you the dispersion, and the resistive part gives you the magnitude. And these two combined, they give you a certain time constant, which gives you the frequency dependence of self-heating. Now, as we know, self-heating is a very slow process, and at very high frequencies, the device does not respond to self-heating behavior. So this is exactly what the capacitance is for. Now, as soon as the device heats, as soon as the device dissipates more power, that is, it operates at very high voltages and very high currents, that power from the device is exported inside the Verilog A code. It's exported to this circuit. Now, this circuit then runs a current through the system, which is with the magnitude of that current proportional to the power dissipated in the circuit. Now, once you have a current running through the system, then that current goes through this resistor and creates a drop. Now, as I said before, the drop in a thermal circuit is not voltage, but it's temperature. So the temperature, not the voltage, but the temperature at this thermal node starts to increase. Then what we do is, now what we have done basically is we have converted power into temperature. So the more power that is dissipated in the device, the more temperature that will rise at this point, at this node in the thermal circuit. and this temperature rise is determined by the thermal resistance RTH. Now this delta T is then fed back to the electrical component of the Verilog A code, which then increases the intrinsic device temperature, this T, and this T is used in all the model equations. Now what is happening is there is a feedback from the electrical part of the Verilog A code to the thermal part, which governs the temperature change, and the rate of temperature change is then determined by this resistor RTH. And in the model, this resistor RTH is defined by a parameter RTH naught. So RTH naught defines the value of RTH, and CTH naught defines the value of this capacitive part of this network. So with these two in place, you get a self-heating model which governs the temperature change with increasing power dissipation in the device. Now, in order to extract this from the model, what we do, we now come to the characterization part of the self-heating, and the way to do this is to have different DC characteristics of the device at different temperatures and pulsed characteristics of the device at different temperatures. Now the pulsed characteristics have to be at a quiescent condition of 0, 0, such that the drain voltage is 0 and you have no current flowing through the device. And when you have no current flowing through the device, you have no power dissipation in the device, and that's going to be used in the maths that's going to follow. Now, once you have these different temperature measurements, both DC and pulsed, what you need to do is you need to take a DC measurement at a low temperature and a pulsed measurement at a high temperature. So basically both of these will be at the same bias condition but at different temperatures. So both of them will have the same VG, will have the same VD, but then the temperatures would be different, and you look for the intersection point of these two curves. Now at the intersection point, since the bias conditions are the same, the junction temperature will be the same, and that's what's going to be used to extract the thermal resistance. If we define junction temperature as the nominal temperature plus the delta T, which we discussed in the last slide, then delta T is thermal resistance into power dissipation. Once you have the junction temperature same at this intersection point, then if you equate these two, and P dissipation for the second case is 0, since the pulsed condition has no current flowing through it, so there's no power dissipation. So what you really get is a way to extract RTH. So RTH is given by the delta of the two temperatures, so T norm 2 minus T norm 1, and then delta PDIS is basically just PDIS 1. So because PDIS 2 is 0, so you come up with RTH is equal to delta T norm divided by P dissipation in the first case. Now this is how to extract this theoretically, but it's even easier if you have IC cap. So what you just have to do is you have to take these measurements into IC cap, and then you simulate using ASM-HEMT. Now after you simulate using ASM-HEMT, the first thing you have to do is extract the model at the nominal temperature. That is, say if you did the measurements at 25, you extract the model at 25. Then after extracting the model at 25, you fit the other temperatures by doing a temperature model extraction, which we discussed earlier. Once you're done with that, once the model has been extracted for different temperatures, then the last step is to have the model at these bias conditions and to tune RTH naught till the simulated curves and the measured curves of the DC component, the overlap. Once you're done with that, you have a number for RTH naught, So that's basically your thermal resistance. That's how it's extracted. The CTH0 can be extracted using the transient simulations. If you have a transient, if you have a pulsed transient, then the decay time of that pulsed transient will give you the CTH0, and you can simply use ASM to simulate a pulse, and then you have a measured pulse, and then again just tune CTH0 so that the two pulses overlap. Now the last section which we're going to discuss are the trapping models in ASM-HEMT. We'll see how trapping has been modeled in ASM-HEMT and how to extract those trapping parameters using pulsed measurements. Now ASM-HEMT has multiple trapping models incorporated into it, 3 to be precise, and each of these models is set to cater to a specific application. So we'll discuss, we will start with trap mod 1, which is defined by this sub-circuit. And trap mod 1 is a trap model which depends only on the drain voltage. So it takes drain voltage as an input and it creates another voltage called VCAP, which is then used to calculate whether or not trapping should be included in the model or not. So the way it works is at high VD values, you have a high VCAP created, and a high VCAP then corresponds to a significant shift in any of the values, any of the effects which is governed by this model. Now, the reason it works only at high VD is because the actual trapping phenomena, they take place at higher drain voltages, where the fields are significant, and then there's a significant trapping in the device. So once you have a VCAP, high VCAP, then you have a significant value of this exponential. Then you can control the effect. You can control the effect of this exponential by using these parameters: B-trap, like B-trap eta naught, B-trap RD, B-trap RS, B-trap V off. So this model then controls 4 different aspects of ASM-HEMT. It can change the threshold voltage, it can change the source resistance, it can change the drain resistance, or it can change the Dibble parameter based on what you need or what you see in the measure data. And the interesting part is that this VCAP is now due to this diode, it's power dependent. So once you have a high RF power signal coming in, that high power RF signal will generate a high VCAP value. And if you have a high power RF signal, then you'll have a significant shift in these values. So it's very suitable for RF applications, and it scales with the input RF power. So basically, when you have high power levels, you have more trapping, and you'll see more effects in the device performance. The next model we have is trap mod 2, and this one is used for pulsed IV applications where you want to simulate pulsed IVs accurately. And in this case, we have 2 different sub-circuits which are being used, and one is gate voltage dependent, the other one is drain voltage dependent, and then there's a simple RC circuit which we then use, and the 4 parameters it governs is the threshold voltage, then the eta naught, and you have the CDS-CD, which, if you remember, is the drain bias dependence of the subthreshold slope, and then it also affects the drain side access region resistance. The interesting part about this is that it now depends on both the gate voltage as well as the drain voltage. So you have both, you can now cover both gate lag as well as drain lag. Now the third model we have is Trap Mod 3, and this is made specifically for power devices, and the only parameter which we change in this one is the drain side access region resistance. So the goal here was to capture the dynamic RON accurately, and for that we also have a temperature dependence in this, as temperature is really important in power devices since they tend to heat up very much, and there should be a proper temperature scaling even for trapping. So that's what we've done with this model. Again, this model depends on both the gate voltage and the drain voltage. Then it affects only the drain side of the access region resistance. For the extraction part, we extract the pulsed measurements from we extract the trapping models from the pulsed measurements. So once you have your DC, once you fit your DC at different conditions, at different temperatures, and then what you do is you take your pulse measurements, and then without the trapping components, you'll see that there's a mismatch because of trapping. Obviously, the measured results don't really fit with the simulation which you have extracted from the DC part. Then what you need to do is then you switch on one of the trap mods, then you start tuning these values. You either try to change the RS, you try to change the RD, or you try to change the V off with different bias conditions. And what you'll see is that the model will start capturing the effects of those trapping phenomena. And this is one validation we have for Trap Mod 2. This was a power device which we had, and again we did the extraction for different pulse conditions. For Trap Mod 2, we had pulse condition of 20 volts 90 milliamps, 20 volts 9 milliamps, 5 volts 90 milliamps, 5 volts 9 milliamps. So these are different quiescent conditions. Remind you, these are different quiescent conditions at which the pulses were generated, and then as we can see, the model is very accurately able to capture all these pulsed conditions. So the way we did this was you start with the DC, and then you have all the pulse measurements, take them to ICCAP, and just although it's a bit slow, but then you can always get it to work, and you can extract these different parameters. This is what we did for Trap Mod 2, and again, I mean, very clear overlapping results with the ASM-HEMT. I'll end my presentation here with the list of applications which are related to ASM-HEMT. So if you want, you can look at them, all the graphs, all the equations, you'll find them in one of these papers, and even the trapping part or the self-feeding part you'll find in one of these papers. And thank you all. If you have any questions, feel free to drop us an email, and we'll be very happy to help. Thank you.